Now, we will be discussing about the solid liquid extraction, that is the fourth chapter, that is we can say whatever we have learned in chapter 3, that is the liquid extraction. In place of this liquid, the carrier this one, in place of the carrier solvent, it is a solid inert, like the inside this one the target component is there, and we are adding the solvent from the outside, extracting solvent, and then the remaining processes will remain same. Okay. So, the solid liquid extraction or leaching process, we can say leaching is the separation process of the soluble constituents of a solid material using a we can say suitable solvent. The basic steps of the leaching or solid liquid extraction process are like intimate contact between the solid feed and with the solvent, then separation of the extract from the exhausted solid, then separation of the solvent like this and entrant solid from the extract, followed by this purification of the product, and recovery of the solvent from moist solid just by pressing or squeezing like this and then drying. Okay. Like the solid liquid extraction equilibrium, it is equivalent to that of the liquid extraction equilibrium, like this concentration of the solute in the clear liquid, that is we can say overflow, then concentration of the solute in the liquid in the slurry, that we say this one underflow, or we can say this one like carrier solvent, here is this we can say inert solid. So, that is we can say underflow. The mass fraction of the species in the overflow, that is y, and mass fraction of the this one species in the slurry, that is we can say x. We are more interested in the overflow. Okay. So, the two common techniques for the representing solid liquid extraction equilibria data actually is, we can say one is this triangular diagram, another is the Ponchon-Savary diagram. Like this a triangular diagram, like this just like we can say right angle triangular diagram, that is overflow actually lies in this we can say BC line, and underflow lies in between this one, and all the tie lines actually originates from the we can say A point, okay, that is we can say inert solid point. Okay. Or for Ponchon-Savary one, say we can say this in the XC and YC, most of the overflow points actually will be like coinciding, but values are very less small, and underflow lines are will be like this one with high values. Okay. Like this single stage operation, that is we can say for extraction whatever we have discussed, the same thing is applied here, means we can say in leaching process. Suppose we have this solid to be leached, means this is we can say one particular solid with insoluble A mass insoluble or inert is there. Then here actually in leaching process we are adding this leaching solvent like extracting solvent. Then underflow will be there, we can say where the inert will be coming with this small amount of this one target component say C, and the overflow will be there, that is actually our interest like this. Okay. Like this we can say this insoluble carriers, this one A like equivalent to carrier solvent in the liquid extraction process, then pure solvent that is actually added like this extracting solvent, then soluble solute, that is the target component present in the inert. And we will be doing the mass balance like F plus S is equal to V plus L is equal to M, and if we do the solute balance, then F x C F plus S y C S is equal to V y C V plus L x C L, right, that is nothing but is equal to M x C M, that is the mixture. Okay. So, x C M will be like this F x C F plus S y C S by F plus S or mixture. Okay. That is we can say F also we can say. So, using Ponchon-Savary, it means like that inert free basis, the underflow or leached solid will be like this, capital X C will be like small x C by x B plus x C, and Z L will be say this underflow will be x A by x B plus x C, whereas the overflow, that is the important one, y C is equal to say capital Y C is equal to small y C by y B plus y C, and Z V, that is overflow, that is y A by y B plus y C. Okay. Like this multi-stage we can say leaching operation similar to that of the extraction process. So, suppose this feed is entering and extracting solvent is added, then we have this overflow, then underflow. That underflow of the stage 1 will be the feed to the stage 2, then again we are adding solvent and then we are getting overflow, like that is continued. Okay. And in case of the multi-stage counter current leaching process, so here we can say feed is entering at stage 1 and solvent is adding from the last stage, that is the NS stage, and the procedure is same like whatever we have discussed in case of the solid liquid extraction process. Okay. And another point actually we discussed this under this solid liquid extraction process or leaching, that is the supercritical fluid extraction. That is we can say in this, in case of this we can say this one what is called PVT diagram. Suppose this above a critical particular temperature and above a critical pressure, there is one zone where it is actually to behaving as we can say supercritical fluid. So, a fluid is called supercritical if both temperature and pressure are above critical point. Okay. CO2 is useful solvent for the supercritical fluid extraction process. The this one state and density of the CO2 is shown on pressure temperature plane. Then supercritical fluids are known to provide this good we can say reaction medium due to their this capacity to homogenize a reaction mixture, high diffusivity, and we can say control phase separations and distribution of the products. So, that is we can say one of these green extraction process with this high efficiency. Physical and thermal properties of the supercritical fluids are like this. Liquid like densities are there for the supercritical fluid, then reduction in the surface tension, then gas like viscosity that is required, then gas like compressibility also, that is also good, and diffusivity value actually is higher than the liquid, and we can sometimes we can say the extraction ability is so many folds higher than that of this liquid. Okay. And now we will be discussing this membrane separation technology. There this we have already discussed these fundamentals of the membrane separation processes, like say if we say this is the process, then feed is entering and we are say suppose applying energy or matter, then products are actually formed like this. So, for that we described this membrane as this phase separating two streams like this feed and product, that allows the preferential transport of a species through this barrier. Okay. Generally we say the semi permeable barrier, and it preferentially separate a particular component and means resisting one and allowing the other to pass through it. The relevant driving forces are like pressure gradient, then we can say concentration gradient, then electropotential gradient, etc. Like this the materials are like this polymeric, liquid emulsion, then some inorganic like this like ceramics and metallic. Okay. So, in separation processes so far we have learned about this we can say humidification, then dehumidification, then drying, then say we can say this extraction, leaching, adsorption say or and other processes. Most of the processes are actually we can say equilibrium separation processes, like product species equilibrium the distribution are in equilibrium, like say we can say distillation or absorption wherever we can say this one, the separation is controlled by the equilibrium. When the process reaches its equilibrium, then we can say this physical separation stops and we need to break the equilibrium, so that the we can say this we get the separation. But now in membrane separation processes we will be learning something about different thing, like it is the rate governed separation processes. Composition of the product and extent of separation are actually governed by the physical transport of the species through the interface. Like we can say reverse osmosis, ultrafiltration, nanofiltration, microfiltration, etc. and recovery of non volatile solutes, like we can say sometimes we can say from the aqueous solutions in hydrometallurgy, These are all we can say rate governed separation processes. Their equilibrium is not we can say this established at all. Like this we can say this types of motion of the molecules through the membranes, that is one is the permeation, we can say DDD concept. Like this diffusion of the solutes in the upstream phase of the barrier, and then diffusion through the membrane, and then desorption in the downstream. And another one is this we can say Knudsen diffusivity, say when the mean free path of the gas molecules especially is greater than that of the pore diameter through which the gas will be permeating, then forward movement actually is done by collision, and then Knudsen diffusivity actually or Knudsen diffusion controls the transport of the we can say gas species through the pores, and there actually we know that say dP by gamma lambda that is less than 0.2, or we can say then Knudsen diffusivity value is equal to 2/3 of this ut into Rp, that is nothing but 2/3 of this this one 8 into Rt by pi m to the power 0.5 into Rp. Okay. And in the simplified form Knudsen diffusivity is 9700 into Rp into T by m to the power 0.5, okay, where dP is the we can say pore diameter and lambda is the mean free path, means this distance between the two successive collisions, and ut is the average velocity of the molecules, and Rp is the pore radius, okay, half of the dP, and T is the temperature at Kelvin. Okay, and sometimes these molecules diffuse, this one passes through the membrane pores by convection also. When pores are larger diameter, the viscous flow through the pores is done by this convection also. Sometimes convective this one flow is there also. Then we have learned in detail about the membrane characterization in terms of permeability, that is we can say this one, the ability of the we can say membrane to permeate the we can say solvent through that at a given pressure, and so if we say this, if the permeability value is very high, then it is we can say highly productive, or we can say throughput is very high. Flux values at various operating pressures we can say are measured, and the slope of the flux versus pressure plot gives the permeability. Okay, as per the Darcy's law, we can say J is equal to say LP into del P minus del pi, where we can say this one, this is the driving force we can say, and this flux, that we can say if we plot this one J versus delta P minus delta pi, then you will be getting one slope. This straight line, the slope actually will be getting S is equal to nothing but LP. If we take pure water, then this del pi will be 0. So, we can say LP is equal to J is equal to LP into del P. Okay. And another term actually we have learned, that is this observed retention, how much solute concentration in the permeate stream compared to the we can say feed stream is quantified by this observed retention. And real retention was like this membrane solute solvent interaction parameter, that is defines the selectivity of the membrane property of then we can say this property, this is the property of the membrane solvent solute system. Okay. And RR actually is estimated using this velocity gradient method, or we need to take a star vessel, then with high speed, then we can say this one observed retention and real retention will be same in that case. Okay. Then other important characteristic was like molecular weight cutoff. Then molecular weight cutoff of the is the molecular weight of the granular protein or any other standard we can say monodispersed solute like this, that is like dextran, PVP or PVA, like this 90% of which is rejected by the membrane, that corresponding value actually is termed as molecular weight cutoff. Okay. Then porometry, that is all pores of a membrane may not allow this permeation of the solvent. So, then porometry is useful and a convenient technique for the determination of the size distribution of the active pores in a membrane in the size range of 10 to 100 nanometer. Okay. Now, the basic forms of the we can say transport like this, one is this facilitated transport, like this carrier mediated transport, and like this we can say first one like this A plus C, that will coming as C A, and it will be transporting to this opposite side of the membrane, and then it will be separated into C and A, and carrier will be coming back to the we can say this back side of the feed. And then we can say this is we can say carrier mediated transport. Whenever we will be talking about this coupled transport, this coupled transport actually has some similarity with the facilitated transport, except that of the complex BC. Okay. Forms on the downstream surface like this one, where only C came back in case of the facilitated transport of the membrane by reaction with the species present in the permeate site of the liquid. Okay. This species diffuses through the membrane, reaches the upstream surface, reacts with A and releases C like this in this case. Okay. So, feed side we have this A plus B C like this, we can say A plus B C we have, or like B plus C whatever may be, then C A will be transporting, okay. Then A C will be there and B will be there, and permeate side A C is coming here and then reacting with B to release A, and then B C will come back. Okay. So, A is transported from feed to permeate side and B from permeate to feed side. Okay. So, the phenomena is called this coupled transport. Okay. Now, this active and passive transport is there through the membrane like this, these are the basic form of the transport. Active transport processes usually work against concentration gradient, this pumping molecules from a lower concentration on one side of the membrane to a higher concentration on the other side like this. So, that is why we can see this one, that is active transport is an important phenomena in biological systems. Movement of like sodium plus and potassium plus ions through the cell membrane of red blood corpuscles against the concentration gradient is example of this active transport. Transport of glucose like this and lower concentration into liver cells like at the higher concentration also. On the other hand, this passive transport does not require any form of this metabolic energy from the we can say the cell wall. This force is the gradient of the chemical potential, okay, like this pressure, temperature, concentration, electrochemical potential. So, this is known as simple diffusion. Okay. So, like this is the passive transport. So, now this manufacturing of the membrane like this preparation of the polymeric membrane, there are so many techniques. So, one major or important technique is this phase inversion technique. It involves the precipitation of polymer from the polymer rich casting solution induced by the solvent and non-solvent miscibility. The polymer creates the membrane structure and the non-solvent actually makes the pores. Okay. And another process is the electrospinning process, like this fiber spinning technique, depending on the electrostatic force that you can say these fibers are formed. Then an electric field is created between the needle tip and the collecting plate by applying the high voltage supply, and then from there actually using the swinning the film actually is formed. Then functionalization of the membranes for specific applications, this one is a very we can say this standard technique. Membrane modification can be done using these different techniques such as this physical coating or blending, graft polymerization, then plasma treatment, chemical treatment, etc. Then graft co-polymerization, that is also one important we can say manufacturing process like chemical modification method by introducing this radical on the polymeric surface like this using this UV or gamma or electron beam or plasma or ozone or hydrogen peroxide. This graft co-polymerization also is done for the polymeric membranes. Now, this for ceramic membranes, the preparation of ceramic membranes are done by mostly the suspension preparation, where the starting powders are mixed with the suitable binding liquids. Then forming is done, this includes the shaping of the prepared suspension according to some predetermined methods. Then heat treatment is done, this means this one using high temperature to bind the membrane particles through sintering process. Then some common methods are like this paste method, like this precursors are mixed together with water solvent to form this paste, then proper shape is given using the dies. Okay. Another one is the dry compaction method. The precursors are mixed with mixed together in, we can say this on dried form. The resulting powder actually is fed into the mold to give it a proper shape. The obtained structures are actually finally sintered, or we can this fired. Okay. Another one is the deep coating method, like this ceramic supports are dipped in polymeric solution and then calcined, means it is then burnt actually. And the another important method is this is extrusion. The ceramic mixtures are mixed with the water or solvent and then fed in extruder. The resulting structure are then say burnt actually. Okay. Then we have already discussed in detail about the limitation of the membrane separation processes, like this we also highlighted that the fouling is the major drawback of the membrane separation processes, because as this is the rate governed separation processes, with time the solutes will be deposited on the membrane surface and then fouling will take place. Okay. And that fouling may be of two types, like one is the reversible fouling and another is the irreversible fouling. The reversible fouling is due to this concentration polarization, or we can say deposition of the solutes on the membrane surface, and irreversible fouling as is called is due to the permanent pore blocking. Okay. For this concentration polarization, say so we can say osmotic pressure is developed, then we can say viscosity pressure will be increasing, then we can say diffusivity will be decreasing, then partial or complete we can say pore blocking will take place, then phase separation also will take place. Okay. Then due to this osmotic pressure development, we can say driving force will be decreasing, because you see driving force was del p minus delta pi, as it is increasing. So, we can say the del p minus del pi will go on decreasing, then extra resistance will be created and permeability will be decreasing, and ultimately we can say this reduction in the permeate flux. So, that is we can say one of the drawbacks. So, there are so many methods to decrease the fouling of the membrane separation processes. Now, these different modules we have discussed in detail about this, say models like this osmotic pressure model, then gel polarization model, resistance in series model, solution diffusion model, and then Hermier pore blocking model. And then we have discussed in detail about the fundamentals of the electric field enhanced separation processes in the membranes, and for that actually initially we discussed about the electrokinetic effects, like the when one charged phase has a relative velocity over the second phase, number of we can say phenomena actually occur. This phenomena in general is grouped as electrokinetic effect, like this. Okay. So, for that we discussed about the origin of the electrokinetic effects, like if a charged phase like this, suppose this phase 1 is placed next to another phase like this phase 2. So, then there is an we can say this excess charge close to that of the interface, and the balancing charge is distributed like this. So, we can say suppose this plus minus these will be distributed, and we can say, and then we have discussed about the categories of the electrokinetic effects like electrophoresis, electroosmosis, streaming potential, then sedimentation potential. Okay. Then we have discussed in detail about the surface and shear and surface of the shear and the zeta potential. So, in electrophoresis these particles like this we can say these spheres or cylinders move in the liquid, and then surface of the shear is an imaginary surface actually, which is considered to lie close to the solid charged surface, and within which the fluid is stationary or having this infinite viscosity. Okay. Now, this film, this thin film layer actually of the fluid is known as the Stern layer. Okay. And so, when particles move, they take an envelope of these liquid fluids with we can say counter charges with it. Okay. So, the potential on this outer surface is known as this zeta potential, and the measurement of electrophoretic mobility gives a measure of this we can say this one net charge actually on the solid particles. Okay. and we have discussed in detail about the significance of the zeta potential, like many colloidal systems are determined by the particle charge, or we can say this potential, and potential distribution determines the interaction energy between these particles. It is responsible for stability towards the coagulation, sedimentation behavior, flow behavior of these we can say mineral ores, etc. Okay. Then we have discussed in detail about the micellar enhanced ultrafiltration, where we can say if the surfactants are solubilized over their critical micelle concentration, then micelle is formed. Then we can say these micelle will be able to trap the solutes and then makes the big globules. Okay. Then we can see this one process with full scale commercial utilization. Examples are like froth flotation is there, process with some commercial applications like this adsorptive bubble separation or liquid membranes are there, and laboratory processes with high potential like this micellar enhanced ultrafiltration MUF, then cloud point extraction CPE, and then surfactant enhanced carbon regeneration ACCR. Okay. Then in surfactant based separation process or MUF, there actually we have discussed the surfactants are surface active agents like maybe ionic surfactant, then non-ionic surfactant, and say Juiter ionic surfactants are there. But ionic surfactants are of two types like this, cationic surfactants like CPC, cetylpyridinium chloride, or anionic surfactants are like sodium dodecyl sulphate or like this, or sometimes this in aqueous solution CPC and SDS both are divided into this one ionic forms like cetylpyridinium plus and dodecyl sulphide minus. Okay. And the factors that influencing the solubilization are like this structure of the surfactant like this and structure of the solubilizate, which we try to trap using this surfactant. Then effect of the electrolyte, then effect of the monomeric organic additives, then effect of the polymeric organic additives, then effect of temperature also. Okay. Then we learned something about the critical micelle concentration. So, that we can say beyond a particular concentration of the monomer, these form globules and enter into the bulk of the solution like this like one globule. So, these globules or agglomerates of the monomers are spherical in shape to have the minimum surface energy and is known as the micelles. So, whenever we say this one minimum amount of concentration of surfactant required to make that micelle is called critical micelle concentration or CMC. Now, we also discussed the determination of the critical micelle concentration for different surfactants, like this concentration of surfactant is plotted with we can say surface tension and osmotic pressure, where it cut actually from there we can say it gives this the concentration of the critical micelle concentration. Okay. So, therefore, the measurement of such properties can lead to the determination of CMC by observing the surfactant concentration, where slope of the curve actually changes, or we can say where like this one, or we can say where the abrupt change in the property takes place, like this may be CMC, or sometimes we can say sometimes when these different properties actually intersect each other, that will also be the CMC value. Okay. So, in case of the anionic surfactant SDS, the outer surface of the micelle are negatively charged, and for the cationic surfactant micelle, the outer surface actually of the micelles are positively charged. Now, in case of the oppositely charged pollutants present in the system, say they will be attached on the outer surface of anionic micelle of SDS like this. The anionic pollutants get attached to the cationic micelles of CPC, CTAB, or we can say this by electrostatic attraction like this. Therefore, for removal of cationic pollutants, anionic surfactants are required, and for anionic pollutants, cationic surfactants are required. Okay. If there are some non-ionic organic pollutants present in the solution, they can be dissolved within the hydrophobic core of the micelle also. That way also sometimes this non-ionic, or we can say some hydrocarbons also are trapped inside the core of the micelle. So, now the transfer of the pollutants from the solution phase to the micelle phase is almost instantaneous. Okay. and say micelles being larger in size, their sizes also increase with solubilization of the pollutant solutes. These larger agglomerates can now be separated by this one more open pore size membranes like this, we can say using ultrafiltration. That is the beauty of this system. So, in fact, there are methods exist to remove the leftover surfactants in the filtered system by suitable chemical treatment also. Okay. So, this is the mechanism of micelle. Suppose this is the micelle, and then suppose the cyanides will be trapped here with the positive part of this, we can say outer surface, and say chromate also will be trapped here, and suppose this we can say this sometimes the hydrocarbons also will be trapped inside this one, or so this one we can say these solute particles will be trapped inside this micelle, and then this will be separated using this more open ultrafiltration membranes. Okay. So, this is the schematic of the micellar enhanced ultrafiltration system using cationic surfactant CPC. Like this, the feed solute and surfactant is added in the MUF system, then retentate will be recycled back to this system, and then using chemical treatment this again surfactant will be separated, and this is the schematic of the membrane separation process. Suppose feed is there, it is entering into this membrane using this pump, and the permeate actually is recycled back to the feed, and whatever retentate is there, it is again coming back to this, we can say this feed tank. Okay. Now, is a quantification of MUF is done by this extent of solubilization S is equal to C0 minus Cp by COS minus CMC, where we can see this is nothing but the amount of solute solubilized by amount of micelles. And for single component system, we have this C0 minus Cp by C0S minus CMC is equal to Q into B into Cp by 1 plus B into Cp, where this Q and B are the coefficient of the isotherm, okay, like this Langmuir isotherm. And this extended Langmuir isotherm type, this equation also is proposed for multi component, we can say this one solute system, like C01 minus Cp1 by C0S minus CMC is equal to Q1 B1 into Cp1 by 1 plus B1 into Cp1 plus B2 into Cp2. And for second component like C02 minus Cp2 by C0S minus CMC is equal to Q2 B2 Cp2 by 1 plus B1 Cp1 plus B2 Cp2. So, 1 and 2 subscripts indicate the solutes 1 and 2. And the sixth chapter is adsorption and ion exchange. So, their adsorption process we explained that this is the surface phenomena, like adsorption may be defined as the selective concentration or retention of one or more components of a mixture on the solid surface. So, adsorption on a solid surface occurs due to the affinity of the surface for, we can say, the particular substance like this. Suppose this is the solid substance and the exposed surface is this one, this is the solid material, the exposed surface is this, and the adsorbed gas molecules has the affinity on this surface, then say these are actually sticked on the outer surface of the solid material. Okay. Or we can say that if we say activated charcoal, then there also say suppose gas molecules will be adsorbed on the outer surface of the active charcoal. Okay. So, the term actually we this one learn, that is adsorbent, like the solid that adsorbs a component is called adsorbent, and adsorbate like this the component that adsorbed on the adsorbent, that is called adsorbate. And this sorption process like this selective transfer of the molecules of the mixture to the surface or in the bulk of the solid is called sorption, or we can say sorption is the combination of adsorption and absorption. Because in absorption in mass transfer operation 1 we have learned this is the bulk phenomena. Now, actually we have learned that adsorption is the surface phenomena. So, combination of these two is called sorption. Okay. And the types of adsorption we have learned, that is physical adsorption or physisorption and chemical adsorption. For physical adsorption process actually a reversible phenomena, which is the result of this intermolecular force of attraction between these molecules of the adsorbent and the adsorbate. And for chemical adsorption or chemisorption, an irreversible phenomena which is the result of this bond formation between these atoms of the adsorbent and the adsorbate. So, we can say physical adsorption is the physical phenomena and chemical adsorption means the formation of the different chemical bond. So, chemisorption process actually requires activation energy. Once it is achieved, it releases a higher amount of energy than physisorption process, because the covalent bond formation in terms of the isosteric heat of adsorption process. Okay. And then we this one demarcated this between physical adsorption and chemical adsorption by these different this one evidences like this. Weak van der Waals force of attraction is there for physical adsorption, but for chemical adsorption chemical bonds are formed. For physical adsorption it favored at low temperature, but chemical adsorption favored at high temperature. Activation energy is not required at all, it is simply this addition of the solvent, this we can say target component on the adsorbent surface, but activation energy is required. And physical adsorption process is highly reversible, but chemical adsorption process is irreversible in nature. And low enthalpy of the adsorption is there for physical adsorption process, but high enthalpy of the adsorption is there for chemical adsorption process. It is a non-specific, but it is the specific in nature, and multi-molecular layer on the adsorption surface is observed, but it is a monolayer is possible, okay, because reaction is taking place, then that active surface is exhausted. And characteristics and the properties of the adsorbents are like this: selectivity, then adsorption capacity, then reversibility, then particle size and its distribution, then porosity and pore size distribution, then specific surface area and structural strength of the and the stability also. Then we discussed about the adsorption equilibrium, like this adsorption and desorption of the molecules occur simultaneously. Then with fresh adsorbent we can say this rate of adsorption is more than rate of the desorption process. These rates actually will be equal and adsorption equilibrium actually is established. So, at a constant temperature we can say amount adsorbed per unit mass of the adsorbent depends on the partial pressure of the adsorbent in gas phase, and the equilibrium relation between the amount of adsorbed, that is Q, and the concentration C of the adsorbate, or we can say the solute at constant temperature T actually is called this adsorption isotherm, that is Q is the function of concentration. Okay. Now, we learned also that types of isotherms are different, 5 types, like this 5. Type A is we can say favorable, and with we can say P by PV, this moles adsorbed actually is increasing constantly. Type B actually we can say BT type means a multi-layer. In the beginning it is increasing, but this rate actually is decreasing after that, like adsorption of the water vapor on the carbon block at 30 degrees Celsius. Type 3, that is we can say unfavorable, that is we can say exponentially it is increasing, like type 4 and 5 actually we can say altering this convex and concave like this, convex concave like this one. So, these are we can say capillary condensation within the pores like this. Now, we discussed about the Langmuir isotherm. There actually we can say the rate of adsorption was related with K1 into P into 1 minus theta, where theta is this we can say how much amount of the available space. And for Toth isotherm we have discussed about this Q is equal to Qm into P by P plus P to the power n and whole to the power 1 by n, okay, where this Qm and B and N, all these are parameter isotherm, these parameters. Okay. And then we discussed about this Fronley isotherm, like this Q is equal to K prime into P to the power 1 by N. In the linear form it is ln Q is equal to ln K prime plus 1 by N into ln P. Okay. There if we plot this one like mx y is equal to mx plus c ln Q versus ln P, then we will be getting one slope. It will be straight line, the slope will give this 1 by n. Okay. And then we learned about this BT isotherm, or we can say this is the multi-layer adsorption, where we learned the details about this Q is equal to Qm into C prime by 1 minus x into 1 plus C prime minus 1 into x, okay, where x is equal to P by PV or partial pressure by vapor pressure. Okay. There we assumed something that heat of adsorption actually remains constant till the formation of the monolayer is complete, and then for secondary layer heat of adsorption is assumed to be equal to the heat of this liquefaction of the adsorbate. Okay. And then we were able to determine the specific surface area, where we can say alpha is equal to 1.09 into m by n into rho to the power 2/3 we have used, where m is the molecular weight, n is the Avogadro number, and rho is the density of the adsorbate. Okay. And Schiff's isotherm, that is we can say one empirical relation, q is equal to q m into k double prime into p to the power 1 by n by 1 plus k double prime into p to the power 1 by n, where q m is equal to we can say adsorption capacity, k double prime is the affinity coefficient, and n is the that is we can say measure of the system heterogeneity. And we discussed about this heat of adsorption values, that is we can say delta H isosteric, like from this Clausius-Clapeyron equation is equal to minus R T square into d ln p by dt is equal to R into d ln p by d 1 by t. So, if we plot this this one what is called ln p differentiation, or we can say this one change in the ln p versus change in 1 by t, we will be getting this we can say this delta H isosteric. Okay. That is d ln p is equal to delta H isosteric by R into d 1 by t. Okay. And adsorption process are like this, stage wise operation is there, and then continuous operation is there, like this single stage operation, then multi stage cross current, multi stage co-current operation was there. Okay. Then in single stage operation we discussed about this amount of adsorbent is very small compared to amount of the solution, and then solute to be removed is adsorbed more strongly than other constituents present, and that is the target also, and adsorption of other constituent can be ignored, and adsorbent is insoluble in the solution. For continuous contacting operation like this, contact operation between the fluid and adsorbent actually are continuous, and we can say steady state mode of throughout this entire apparatus, and this is characterized by movement of the solid as well as this fluid. Okay. And then say multi-stage cross current operation, it is similar to that of whatever we have discussed in case of this extraction leaching. For multilayer counter current operation also this is equivalent to that we have already discussed in leaching extraction. And then classification of the adsorption system like this single transition system, then we have discussed about the two transition system, then we have discussed about the multiple transition systems. Okay. And we have discussed in detail about the dynamics of the adsorption column, and like this single transition system, that differential form is like this, minus dl into del 2 c by del z square plus del z of b into c plus del c del t plus 1 minus epsilon by epsilon into del q by del t, that is equal to 0. Okay. For this one we can say whenever we have discussed about this equilibrium consideration, then one is this like favorable, then one is the linear, and there is another is unfavorable one. For that, say for favorable we discussed that q star minus q 0 prime by q 0 minus q 0 prime, that is greater than c minus c 0 prime by c 0 minus c 0 prime. For linear we have discussed that q prime minus q 0 prime by q 0 minus q 0 prime, that is equal to the c minus c 0 prime by c 0 minus c 0 prime. And for unfavorable we can say adsorption process, q minus q 0 prime by q 0 minus q 0 prime is less than c minus c 0 prime by c 0 minus c 0 prime. Okay. And the classification of the single transition system like this, nature of the equilibrium relationship, then isothermal or we can say near isothermal, then we can say concentration level of these adsorbable components, then flow models, then complexity of the kinetic model we discussed in detail. And then multiple transition system also, there we have done this component balance like this, minus dl into del 2 ci by del z square plus del z of v ci plus del ci by del t plus 1 by epsilon into del qi by del t where I is this ith component. So, we can say this one n number of components are present there. Okay. Then we discussed about the unsteady state fixed bed adsorber. So, suppose this bed is fixed and then suppose the adsorbent is there and suppose adsorbent is entering, then suppose some portions are now saturated, and then with time the saturation zone actually will go on increasing, and say with time one time will be reaching there, say this almost entire part is saturated, and then we have this mass transfer zone actually the remaining part, and it is actually moving like this. The S shaped curve shown is called this mass transfer wave front. Okay. And this breakthrough like this, whenever we say this one, whenever this we can say this concentration of the solute in the effluent actually will shoot up from CD to CE, we can say this one at point D, the lower portion of the adsorption zone has reached bottom of this bed, and we can say the solute concentration in the effluent has suddenly risen to the appreciable value CD. The system is said to have reached the break point actually. Okay. And the portion of the effluent concentration curve between this position D and E is called breakthrough curve. Means the solute in the feed has been able to break through the barrier of the bed of the adsorbent. So, equilibrium time T actually is required to get saturated. Okay. And then we discussed about the pressure swing adsorption process, then adsorption, then depressurization, then purging, and then we can say this one repressurization also we have discussed this one. And the last chapter that we discussed, that is a small chapter like this crystallization process, and for that we discussed in the beginning like the atomic arrangement, then the space lattice like this 7 we can say crystal systems, then we discussed about the various space lattices like unit cell, maximum possible symmetry with the smallest size, then 14 possible space lattices, or we can say under these 7 crystal systems. Like symmetries are like transitional, then rotational and reflexional symmetries must be there in the system. Then arrangement of the lattice points in unit cell like this, we can say simple system, then body centered systems, then face centered system, like these base centered systems or end centered system or hexagonal system. Okay. So, there this terminology is like crystal, that is defined as the solid particle which is formed by the solidification process under suitable environment, in which the structural units are arranged by the fixed geometric pattern. Like then crystallization, that is we can see this process. Then crystal lattice, we can this defined as an orderly internal arrangement. Then unit cell, the smallest geometric portion which repeats to build up the whole crystal is called the unit cell. Then we have this we can say body centered cubic crystal, then we have this face centered cubic crystal, and we can say this hexagonal closed packing. Okay. Like different 7 crystal system like this isometric, then tetragonal, then orthorhombic, then monoclinic, triclinic, hexagonal, then trigonal. Okay. With the different examples. And Miller indices also that is indicated by HKL in this x, y, z in 3 directions. From using this we can say this indices, we are able to designate one particular hexagonal crystal system. Okay. And then we have discussed about the linear density, like number of the atoms centered on the direction velocity direction vector divided by the length of the direction vector. And in case of the planar density, we described about this number of atoms the centered on a plane divided by area of the plane. Okay. And in the crystallization process, we have discussed about the when the crystals are produced by cooling a saturated solution, process is called solution crystallization. When crystals are produced by cooling this molten solid in absence of any solvent, it is called this melt crystallization. Some liquids like this ammonium oleate etc., exhibit this anisotropy at temperature just above this, their melting points are called liquid crystals or LC. Okay. So, major steps in the crystallization process are like crystallization, then separation of the crystals, then washing of the crystals, then drying of the crystal, this one moist crystals. Okay. And the mechanism of the crystallization we discussed about the supersaturation, then nucleation and then crystal growth. Okay. Then say we have discussed about the Gibbs-Thomson equation, this ln C by Cs is equal to 2 sigma into mw by RT into rho C into R, where C is the solubility of the particle radius r, then Cs is equal to normal solubility, sigma is equal to solid liquid interfacial tension, mw is equal to molecular weight, T is the temperature and rho C is the density of the particle. Okay. Since these smaller particles have more than normal solubility, these dissolve even in a saturated solution and raise the temperature, creating supersaturation. Okay. And say the larger particles start growing, actually overall process consists of the dissolution of the smaller particles, making the larger particles grow. This phenomena is called Oswald ripening. Okay. And then say we discussed about the crystal growth, like using this mass transfer theory is the McCabe delta L law, and we this one explained that the precipitation is a solid formation from the solution by rapid and simultaneous nucleation, crystal growth and agglomeration of the particles. Okay. And we discussed about the design of the crystallizer. By this on the feed rate and the state, by the desired crystal size distribution and the yield, like this yield as calculated like this 100 into Qi into Cin minus Qo into Cs divided by Qi into Cin, where Q is equal to feed rate and Q is equal to Qo is equal to the rate of the outflow of the mother liquor. Okay. And then required rate of the evaporation is determined by the solvent balance. So, during this crystallizer design, we considered that with some amount of the evaporation and without evaporation also. Like then crystal volume actually is designed by this equation Wx is equal to 1 minus 1 plus x by x square by 2 plus x cube by 6 into e to the power minus x, that is equal to 0.5. From there actually we got x is equal to 3.67 and Lm actually we got as 3.67 into g into tau, where this Wx is the calculative mass or weight distribution function, Lm is the median size of the cumulative size distribution. Okay. And then we have done the crystallization dimension and recirculation rate also. And some equipment for crystallization are of like batch and continuous. Some common crystallizers are like forced circulation, then draft tube, then conispherical, forced circulation, baffle surface cooling crystallizer, then circulating liquid crystallizer, then tank crystallizer. It is used like scrapped surface crystallizer, fluidized bed, then surface cooled and direct contact refrigeration crystallizer also. So, the references are huge, but say we can use R.E. Travell's book of mass transfer operations published by McGraw-Hill, international edition of 3rd edition like 1981, and McCabe Smith and P. Harriot's book of unit operations of chemical engineering, 6th edition by McGraw-Hill, international edition of 2001. Then B. K. Datta's book of principles of mass transfer and separation processes by Prentice Hall of India on 2012. Then D. M. Ruthven's book principles of adsorption and adsorption processes by John Wiley and Sons of 1984, and Kangley, A. G. Fenn, W. S. Winston Ho and T. Matsura's book of advanced membrane technology and application by John Wiley of Sons 2008. So, thank you very much for your kind this one patience, and good luck for the examination. If you have any suggestions, feedback, I will be happy to receive.